So this is the 6-1 homework. It has been moved to be done Monday at 11:59 p.m. We had a question. I'm going to start with problem number 4. Now, you can ask me other questions here in a minute, but I would like to talk about the domain that they're asking for in problem number 4. Okay. Now, my functions and your functions might be slightly different, but let's just talk about it. In problem 4a, if you think about the numbers, the only number that messes this fraction up that we have to skip is where x plus 5 equals 0. So remember, x plus 5 equals 0 at -5. So the only thing we have to skip is -5. So we're going to go to negative infinity. We're going to skip -5. And then we can keep on going. So our domain for 4a, for me, would be from negative infinity to -5, and then again from -5 to infinity. For part B, x minus 3 equals 0 at 3. So that's the value I have to skip. So I'm going to go from negative infinity to positive 3. I'm going to skip it. I'm going to go from 3 to infinity. Now, be careful with C. When we set, for me, I have a coefficient there. So my 2x plus 4 equals 0. First, I get 2x equals -4. Then I have to divide off that coefficient. So if it divides into it evenly, like what mine did, you just divide it. But be careful with that. So our denominator is 0 at -2. So I can go from negative infinity up to -2. And then I have to skip it because there's a vertical asymptote there. And then I get to keep going. Now, finally, one of the weirdest ones here is x squared plus 6. If we go to try to solve that one, x squared equals -6. So that is never going to happen. So nothing messes this one up. So we get to go from negative infinity to positive infinity. Okay. Okay. So I'm sorry, they didn't like the way I typed negative infinity to positive infinity. Let's see if they like that now. There you go. So that is question number 4. Do we have any questions? Other questions about homework 6-1 that you would like to see? Any other questions about homework 6-1 before we look at 6-2? Okay, so now please at this time go to homework 6-2, please. One of the most common questions I've had about this is question 11 and 12. Now, your 11 and 12 might be flip-flopped versus mine or the person sitting next to you. So, if you do not find that your question 11 looks like this, jump to question 12. Let's at this time look at my 11, which is about a drug concentration in someone's bloodstream. So if it's not your 11, look at your 12, okay? And let's go ahead and do this problem together. It says that the amount of drug in a patient's bloodstream over T hours is given by the function f of t. What happens to the concentration as T increases? So the thing you want to look at, if we look at 41t over 4t squared plus 10, over time, because our lead term is in the denominator, it is going to head to 0, okay? What is the concentrate after 3 hours? I'm just going to let iMath do the work. On the top, I'm going to put 41 times 3 divided by, on the bottom, 4 times 3 squared, and I can just put 9. I can do that part in my head, plus 10. And then if you look at the bottom one, what is the function notation that would represent the concentration of the drug after 9.2 hours? Well, that's just our function f at 9.2. That's all they want there. Okay. So that could have been your question 11. It could have been your question 12. Do we have any questions about my question 11, the concentration in the blood? Okay. Now let's go and look at what might be your question 11 or 12 about the population of deer in a park. So let me write down that equation. So it's 1400 plus 3000t over 7 plus 2t. Okay. So the first says, what is the initial number of deer in the park? Well, if you plug in, so that's P of T for population, I believe. So if you plug in 0, that is our initial population. On top, that would be 1400. On bottom, that would be 7. 1400 divided by 7 is 200. But you can let iMath do that for you if you want. You could just put 1400 divided by 7. How many deer are in the park after 6 years? I'm going to let iMath do that. It's 1400 plus 3000 times 6. That's our numerator. Divided by, and I'm going to put my denominator in parentheses, 7 plus 2 times 6. Now, if they don't like that, the preview says 1021. It when rounded to the nearest whole year. So if they don't like that, I think you could probably just use that preview to your advantage, but they're okay with that value. And then if this says if this trend continues indefinitely, that's really asking you your horizontal asymptote. So what's really cool is since the lead term on top and the lead term on the bottom match, it's just that 3000 divided by 2. 3000 divided by 2 is 1500. You can use those lead term coefficients. So that is our question 11 and 12 from 6-2. Okay, that's your question 11 and 12 from 6-2. And that's that. Okay. Do we have any other questions from the 6-2 homework before we start our 6-3 investigation? So you have till midnight tonight, 11:59 tonight, to get these finished. Please go ahead and finish those. Okay, so now at this time, go into Google Classroom and find the 6-3 investigation about graphing rational functions. The last section we're doing for iMath and for this part of pre-calc is section 6-3. So we are finishing mod 6 by doing the graphs of rational functions. For every single one of these problems, I'm going to do the 5 steps that we see there. So if you want to go ahead and write those down, it will answer all the questions that we have. It says identify the points of discontinuity, the holes, the vertical asymptotes, the x-intercepts, the horizontal asymptote of each. 2 and 3 will give us the points of discontinuity. The points of discontinuity for a rational function are the holes in the vertical asymptotes. So the step 2 and 3 will answer that question for us. So I'm going to do the odd ones with you today. If we have time to finish all the odds, I'll do that. If not, we will continue this tomorrow, okay? So let's take a look at problem number 1. to find the points of discontinuity, the holes, vertical asymptotes, we must have it in factored form. That's why step 1 always mentions to factor it. So I'm going to do this kind of in one fell swoop. I mean, you guys might have to do it in 2. But if you factor out a 3, you are left with x squared plus x minus 6, which is factorable one more time to be x plus 3 and x minus 2. So that's the fully factored form. So hopefully after you factor out that 3, you would see that you would get x squared plus x minus 6, which is factorable one more time. Okay. So factored form done. Holes occur when we have a factor on top that matches a factor on the bottom. The only factor we have on top is a 1, so we don't have anything good to help us. So there are none of those. But a vertical asymptote occurs where a factor in the bottom did not cancel out. So, we have for a vertical asymptote, could 3 equal 0? No. So if there's not an x there, that front number doesn't affect it. But x plus 3 could equal 0 at negative 3. And x minus 2 could equal 0 at positive 2. So we have vertical asymptotes at negative 3 and at positive 2. So the only points of discontinuity for this particular function is at positive 2 and negative 3. And we have vertical asymptotes there. Those are a type of infinite discontinuity. That's an infinite discontinuity. What are the zeros? Well, the zeros occur where the top of a fraction equals 0. Can 1 equal 0? Can 1 equal 0? Nope. So there's none of those. And then finally, we have to remember our rules of horizontal asymptotes. Remember, the rules of horizontal asymptotes requires that we look at the lead term on top and the lead term on the bottom. The lead term on top is a 1, so an x to 0. The lead term on the bottom is a 3x squared. If the higher power is in our bottom, we don't have to do any calculation. It always is y equals 0 for our end behavior. Our horizontal asymptotes always go to 0 when the lead term on the bottom is higher than the lead term on the top. It's degree. So that is problem number 1. Do we have any questions about problem number 1? We good with that one? Okay, let's do number 3. It says that we have to factor in. There's lots of factoring that we would have to do with this. On the top, there is a factor of x that we could remove. We would get x squared minus x minus 6, which does factor to be x plus 2 and x minus 3. Now, I'm doing it in one step. Obviously, you might have to do it in 2. That's okay. In the bottom, I would factor out a negative 3. When you do that, you get x squared plus x minus 6, which gives us x plus, this is what I get for doing it in my head. So we'd get x squared plus x. So that would be plus 3 and minus 2. So we now have it in factored form. There are no factors in the top that match a factor in the bottom. They're super close. But there's nothing that matches the top and in the bottom. So when that happens like that, there are no holes. But there are some infinite discontinuities. There are some vertical asymptotes. The vertical asymptotes are where the bottom factors equal 0. Well, we don't have to worry about negative 3. Negative 3 will never equal 0. If it had an x on it, we would worry about it. But x plus 3 equals 0 at negative 3. X minus 2 equals 0 at positive 2. So we have a vertical asymptote at negative 3 and positive 2. Those are infinite discontinuities at that spot. Those are the only two values that we would remove from our domain, negative 3 and 2. Now, the zeros occur where the top of our fraction equals 0. So that would be where x equals 0, x plus 2 equals 0, and x minus 3 equals 0. So we have a 0 at 0. -2, and +3. Sorry, that looks so ugly. So our graph hits the x-axis at 0, -2, and 3. Now remember our horizontal asymptote, excuse me, our horizontal asymptote requires that we look at our top and our bottom lead term. The lead term on top is x cubed. The lead term on the bottom is -3x squared. When the lead term is higher in the top, think about how it reduces down. That kind of looks like -x/3. That doesn't have a horizontal asymptote. It acts like a line with a slope that's negative. So it would be a negative sloping looking line with some holes and vertical asymptotes and weird things happening, okay? So our horizontal asymptote, it actually is called a slant asymptote that we would be able to find that acts similar to the line -x/3. But there's no horizontal asymptote for that one. So now let's move on to 5. Now we're going to do exactly the same things in exactly the same order. It will answer all the questions and it will also help us graph it along the way, okay? So you'll notice I've written the exact same things because I'm going to get the exact same information from my function. So the first thing I have to do is put it in factored form. They both contain an x, factor out an x. We're left with x times x minus 3. So there is no holes because there are no factors on top and bottom that match. But there is a vertical asymptote where x equals 0 and where x minus 3 equals 0. So at 0 and at 3. So go on to your graph paper. Stop what we're doing. Let's put that information that we have just found on to our graph paper. We have a vertical asymptote at 0. We have a vertical asymptote at 3. Vertical asymptotes you cannot cross over. Vertical asymptotes you cannot cross over. Let's talk about our zeros. The zeros occur when our function equals 0. So a fraction equals 0 when the top equals 0. Well, -4 can't equal 0, so there are none. So we also know that this graph never touches the x-axis. There are no zeros. So put on that line. Let's talk about our horizontal asymptote. The horizontal asymptote occurs at 0 if the bottom power is more than the top. So our bottom power is definitely more because it would be like -4 over x squared. So that tells us that it always goes to 0 when that happens if the lead term on the bottom has the higher power. We already saw that. Here is our horizontal asymptote. The ends will head to 0. The ends will head to 0. This function just happens to not even hit the center of it, doesn't hit the x-axis either. That doesn't have to happen, but in this function it does. So now we have to graph it. We don't have much in the way of points, do we? We just have lots of dashed lines on there. So we're going to graph this function by plugging in some points in this region because we have to have a full curve fitting in this region. So it's probably like that or that. We have to have a full curve hitting in this region. So it's probably like that or like that. We have to have a full curve in this region or this region. So it's one of those things. So let's plug in some points. If we plug in something to the left of 0, I'm just going to plug in -1 and -2. So just plug it in. If you plug in -1, I get -4 over 1 plus 3 which is 4 or negative 1. So go to negative 1 and put the point negative 1. Let's plug in negative 2. We get negative 4 over 4 plus 6 or 10. So it's negative 0.4. So it makes sense that we have to follow this asymptote and follow this asymptote. So that piece is wedged in that bottom left corner. Now, I don't know what's happening in here. The points 1 and 2 are nice in there, so why not plug in 1 and 2? If you plug in 1, you get negative 4 over negative 2 or 2. If you plug in 2, you get negative 4 over negative 2 or 2. So I have to follow this asymptote. I have to follow this asymptote. I can't go so low that I'm here. You could plug in negative 1.5 or positive 1.5 right there if you want, but let's just make a little like parabola-like thing right there. But we know don't make it so low it can't cross this line. So you could make it that far down, but you can't make it touch that because there are no zeros. Okay. Now I need something over here. So why not plug in 3? No, I can't plug in 3. Let's plug in 4 and 5. If I plug in 4, I get negative 4 over 16 minus 12, which is 4, right? 16 minus 12, yeah. So I get negative 1. If I plug in 5, I get negative 4 over 25 minus 15 or 10. I get negative 0.4. So it's almost a perfect little match of this one right here, but going in the opposite direction. So follow the asymptote, follow the asymptote. After you have tried to graph it yourself, plug it into Desmos. Did I get what I expected to get? But you can see, I don't magically have a way of knowing exactly what this function is doing until I plug in points. So once you put on all the information you do know onto the graph, you're going to have to plug in some points. There's no way around it. Even today, my calculus students had a quiz over this kind of graph. If you look at their quizzes, it's exactly what you're doing. The difference is they can pinpoint where the bumps are exactly, the curvature of it, and we can't do that in this class, so we do as much as we can. Any questions on number 5? Okay, let's do number 7 together. We're going to go down the entire list just like before. So I notice that both of those are divisible by negative 2. If you can remove a coefficient, that's helpful. And so you get x plus 3. So I have it in factored form. There's no factor that hits on the top and the bottom, so I'm good to go. There are no holes. I can jump right to my vertical asymptote. Remember, a vertical asymptote is where the bottom equals 0. So if we set our bottom equal to 0, negative 2, we don't have to worry about that, can't equal 0. But x plus 3 equals 0 at negative 3. That's the only point that we skip on the graph. We have pieces everywhere else. Go to your graph paper and over at negative 3, put your vertical asymptote on. Now let's talk about zeros. The zeros of a rational function are where the top of our fraction equals 0, after we've reduced it as much as possible, which we have. So in this case, it's where x plus 4 equals 0, or at negative 4. So go to your graph paper and at negative 4, put a little dot. We know we hit that exactly and only at the point negative 4. Finally, let's talk about horizontal asymptotes for this one. The lead term on top is an x. The lead term on the bottom is negative 2x. They match. So just reduce this down and you'll find your horizontal asymptote. Our horizontal asymptote happens at 1 over negative 2, which is negative 1/2. If the lead term on top and the lead term on the bottom match, use those coefficients, reduce it down, you find your horizontal asymptote. So now go to your graph paper, and at negative 1/2, do your best to try to make it there. We have a horizontal asymptote. So now it's time to just plug in some points. What's great is we know that this piece, if it follows the asymptotes, follow the asymptote through this point, follow the asymptote. So when you have a point, you kind of know where it's locked. We know where it's locked. It's locked in that top left corner. But we sure don't know what's happening over here. So I'm going to plug in 2 points. I'm going to plug in negative 2 and 0. Okay, so if we plug in negative 2, we get 2 on top. We get 4 minus 6, or negative 2 in the bottom, which is negative 1. So at negative 2, we're at negative 1. If you plug in 0, you get 4 over negative 6, which is negative 2/3. We're just under that asymptote. And it makes sense now because we got to follow this asymptote, hit those 2 points, and keep getting closer and closer to that one. So that's how we graph problem number 7. So there's problem number 7. Do we have any questions about how we did number 7? Okay, so we're going to continue this tomorrow. We're going to keep going on this, but whatever we have left, we'll do tomorrow. You are going to have an assignment over graphing, in a worksheet and a video that I will post after Thanksgiving, and then a iMath assignment as well over 6-3 over the graphs. So graphing isn't going anywhere. For those of you that are not CCP students, you will have a test over 6, 1, 2, and 3. And for those of you that are a CCP student, it is included on your final exam. Okay, let's take a look at problem 9. We're going to get it in factored form. On the top, I can take out a 3 and an x, and then I'm left with x minus 4. The bottom is a nice factorable piece. That is x minus 3 and x plus 1. So I have it factored. I know we haven't come across one with a hole in it. I think that'll happen eventually. But there's no factor on top that is a match on the bottom. So there's no hole. But there definitely is a vertical asymptote. Remember, a vertical asymptote occurs when our bottom reduced form equals 0. So that's where x minus 3 equals 0 and x plus 1 equals 0. So at 3 and at negative 1. Now, if I'm asking you to graph it, which I am, do not go further until we go to our graph and we put a vertical asymptote at 3 and a vertical asymptote at negative 1. So those vertical asymptotes make it so we're going to have a piece over here and a piece here and a piece there. I don't know what the pieces look like, but you know. I should have 3 distinct pieces of my domain and my graph. So vertical asymptotes are done. Zeros. Zeros are where the top is equal to 0 if it's reduced as much as possible, which it is. So where does 3x equal 0? Where does x minus 4 equal 0? And that would occur at 0 and at 4. Put those points on. I hit the x-axis only in 2 spots, at 0 and at 4. Last thing we have to do are the horizontal asymptotes. The lead term on top is 3x squared. Lead term on the bottom is x squared. When they match, we just get to reduce that. 3x squared divided by x squared is 3. So our horizontal asymptote is y equals 3. Put it on our graph paper, but put it on very specifically. Put it on the left side and the right side. Now, you could put it all through the entire thing. That's okay. Just remember that the center of the graph can violate a horizontal asymptote. It doesn't have to never touch it. It's just those ends that'll head toward it. So our middle can possibly go like that or like that. I mean, it can possibly go through our horizontal asymptote. Horizontal asymptote only predicts our ends, not what's happening necessarily in the middle. The middle can do what it wants to do. Okay, so what's ready to do? We're ready to graph this. It appears as if this piece is stuck down here, but since it's so far away from our asymptote, why not plug in, let's plug in 5. You can plug in whatever you want, but I'm going to plug in 5. If I plug in 5, I get 15 over 12, I think. Let me do that one more time. So if I plug in 5, I got 15 on the top, that's right. And on the bottom, I get 2 times 6, I get 12. Yeah. So it's just a touch over 1. So go over to 5. We know it's a touch over 1. Oh, that helps me. This piece now is going to go like that. Okay. Now I need to know what this thing's doing. Am I going up, then back down? Because I got to follow the asymptotes. Am I going this side up and down? Am I going both up? Am I going both down? I don't know. So let's plug in. Let's plug in 2. So if I plug in 2, I get 6 times negative 2 on top. And I get negative 1 and 3 on the bottom. I get 4. So at 2, I'm at 4. Now I'm going to plug in negative 1/2 just to see, does it go down here after it hits that 0, or does it go up and make like a parabola, sort of like a lopsided parabola? I don't know. If I plug in 0.5, let me tell you what you get. I'm going to throw that into a calculator. I get 1.4. So if you plug in negative 1/2 into a calculator to our original function, you get 1.4. So it does kind of make a little lopsided parabola there. So at negative 1/2, it's at 1.4. So it's kind of doing this little lopsided parabola there. Again, the center portion of our graph can do whatever the heck it wants. And then finally, I need some points over there somewhere. So let's plug in negative 2 and negative 3. If I plug in negative 2, let me tell you what I get. I get 36 in the top. Over 5, which is 7.2. So go over to negative 2, I'm up at 7.2. If you plug in negative 3, let me tell you what we get. I get 5.25. So this piece is right here. They're gross. They're weird. These graphs. I can't tell you much except put on the information you know and plug in more points to find the pieces you don't know. I mean, that's the easiest way that's the way I do it. And I've been doing these types of graphs for a long, long time. Do we have any questions about number 9? I'm going to leave that there for a minute. Make sure everybody has their graphic written down. Let's do one more, okay? Let's do number 11. I want to get to one that has a hole in it. Yeah, this one won't either, but let's take a look at number 11. So if you factor the top, you get x times x plus 2. If we remove a negative 4 from the bottom, we get x minus 2. We have factored it. There's no holes because there isn't a factor on top and bottom that match. Maybe tomorrow's ones will have a hole in them. Let's talk about our vertical asymptote. Our vertical asymptote, remember, is where the bottom equals 0. Negative 4 doesn't equal 0, so we don't have to use it. There's no x there. We just have to be concerned with x minus 2 equals 0 at 2. Stop what you're doing. Go to your graph paper at positive 2. Put your dashed vertical asymptote. Let's talk about the zeros. The zeros occur when the top of our fraction equals 0. So at 0 and at negative 2. Stop what you're doing. Go to your graph. Put those 2 points on 0, negative 2. What about our horizontal asymptotes? If you take a look at our lead term on the top, it's x squared. Our lead term on the bottom is negative 4x. There are none. But when the power on top and the power on the bottom are exactly 1 power apart, when the power on the top is exactly 1 more on the bottom, we're going to get, for the first time, something called a slant asymptote. Now, what a slant asymptote is it's almost like you took a horizontal asymptote and you tilted it. And we will follow that instead. And how do you find it? Well, we're just going to take x squared plus 2x. We're going to divide it by negative 4x plus 8. And we're not going to care about our denominator. So what times x squared, what times negative 4x would give us x squared? Well, that is negative 1/4 x. And I'm going to show you a other little trick to find the slant asymptote in a minute. And then when we do that, let's do our actual division. We get x squared minus 2x. We're subtracting, so change the signs of both. We get 4x plus 0. And then we get what times negative 4x would turn it into a positive 4x? That would be negative 1. And then stop. We don't have to go any further because we don't care about the remainder. This is our slant asymptote. So y equals negative 1/4 x minus 1. Now, how do you graph that? It's a line. Graph it. But just make it a dashed line. Okay. So we're going to start at negative 1. We're going to go down 1 over 4. We're going to connect that, but with a dashed line. That's a slant asymptote. Now, I'm not going to be super concerned about slant asymptotes, but slant asymptotes are a thing. So I want you to be able to find a slant asymptote. But again, it's not my biggest concern about life. And then let's kind of show you what the graph looks like. So it has to follow this asymptote, hit those 2 points, and follow this asymptote. So it's wedged in there. And what's interesting about these, most of the time, there'll be a mirror wedge. Like if you make an X, it should be, I expect our other pieces down here in that little section. Okay. So the only thing I need is that piece, what's going on in there. So let's plug in 3 and 4 to our function. If you plug 3 into our function, on top, we get 9 plus 6 or 15. And on the bottom, we get negative 12 plus 8, which is negative 4. 15 divided by negative 4 is negative 3.75. So remember how I said that it should be in this little section, and it is. If you plug in 4, you get 16 plus 8. 16 plus 8 is 24. You get negative 16 plus 8, which is 8 or 3. Wait, I should get a negative. Let's see. Let me do it one more time. So we would get 4. Yeah, we would get negative 8. So that's negative 3. So at 4, we're down at negative 3. And then we're just doing this. Follow the asymptote, follow the asymptote. So slant asymptotes are really kind of interesting how they work. They just think about if this was a horizontal asymptote, it just got tilted. So what normally might have been here, a slant asymptote slants, and it still wedges our graphs in those sections. So hold off on turning this in. We are going to continue this sheet together tomorrow. Please, for a few minutes that you have left, you don't have much, but a little bit of time, look at your 6-1, 6-2 homework in iMath. Do you have it done? It is due tonight by midnight. Okay, so please work on that. Hold off on turning this in. We'll turn this in tomorrow.